This video lecture will cover the last part of Chapter 16. We'll start off with this slide discussing factors that affect acid strength. And this is important to note. This is for binary acids only. So binary meaning H and one other element. So as we can see, acid strength increases going down and to the right. For example, HCl is a stronger acid than HF. I know that because HCl is a strong acid, right? One of the strong that we memorize. HF is a weak acid, so that helps me remember the trend. I also know it increases to the right. HF is an acid, H2O we don't think of as an acid at all. So again, what we're looking at, the elements in order on the periodic table, right? Carbon, nitrogen, oxygen, fluorine. You add an H to make a stable molecule, and then you consider it as an acid or a base. Also, H2S is a weak acid, HCl is a strong acid. So that helps me remember it increases to the right. And we can also look at the base trend is the opposite. So base trend increases up and to the left. So for example, NH3 I know is a weak base. pH3 is also a weak base, but because base strength increases up, NH3 is a stronger weak base than pH3. I know that they're both bases because NH3 has, right, a lone pair. So my Lewis structure of ammonia, NH, H, well, pH3 will be the same because phosphorus and hydrogen have the same number of valence electrons. But NH3 is going to be a stronger base. We can think of that electron group as being a little bit bigger and more willing to accept a proton than the lone pair on pH3. So here looking at factors affecting acid strength, we're looking specifically at this case for oxyacids. So oxyacids meaning we have an acid where oxygen involved, and what makes an acid an acid? A weak bond to hydrogen. And in this case, that is a OH bond. So the weaker the bond to the hydrogen, the stronger the acid. So the weaker, we'll call this the OH bond. So it's that bond right there. The stronger the oxyacid. So what makes the bond weak? If I have electron withdrawing groups next to it. So I can think of this chlorine as pulling electron density away. So that chlorine is pulling electron density away, making that OH bond weaker, and so is the iodine. But if we think about our electronegativity trends, and remember my electronegativity trends for the periodic table, increase to the right and up. Electronegativity is the ability for an atom to pull electrons towards itself with an equivalent bond. So I know that iodine is farther down on the periodic table. The electronegativity values are listed here. So farthest down on the periodic table and highest up. So the farther to the top right, the more electronegative. Therefore, chlorine is going to pull more strongly than iodine, which makes HClO a stronger acid than HIO. And I can see that because my Ka value, right? The larger the Ka, the stronger the acid. And that's seen there. So on that same trend, looking at factors affecting acid strength for oxyacids, I know the more electronegative the atom, the more strongly the electron density is being pulled away from that OH bond, making it a stronger acid. Well, here I can think about having more electronegative atoms. So again, this is the bond that needs to be weak to make it an acid. So the more electron withdrawing groups, the stronger the acid. I know that perchloric is a strong acid, and I can think of, I've got that chlorine pulling, and I also have 3 other oxygens pulling. So that's a strong acid, so we have 100% dissociation. So for chloric acid, I have not only the chlorine, but also 2 other oxygens pulling electron density away, making that a weaker bond, making that acid not quite as strong as perchloric because there are only 3 oxygens versus 4. Chlorous acid will be weaker with just chlorine and the other oxygen, and then hypochlorous will be the weakest with the smallest Ka, the fewest the oxygens. So for a series of oxy acids, if you have the same central atom, in this case chlorine, the more oxygens we have, the stronger the acid. So practice exercise 18. In each of the following pairs, choose the compound that leads to the more acidic, less basic solution. So thinking about the trends on the previous slides, go ahead, pause the video, think about your answers, and then hit play, and we'll go over it together. Okay, so thank you for pausing. We're looking for the more acidic solution. So HBrHF, I know HBr is more acidic because it's a strong acid. HF is a weak acid. Also, I know acid strength increases going down the periodic table. More acidic. H2S, this I know is a weak acid. And this is a weak base. So it's definitely not as acidic. And also, I remember my acid trends increase to the right on the periodic table. HNO3 is going to be a stronger acid because it has more oxygens. Also, it's a strong acid that we have to memorize. HNO2 is not, therefore it's weak. And lastly, H2SO3 is going to be a stronger acid than H2SeO3. All of the atoms are the same except for the central ones. So comparing just the central atom sulfur to selenium, sulfur is more electronegative than selenium, so H2SO3 will be a stronger acid. Again, for a series of oxy acids, the more electronegative the central atom, the stronger the acid. Again, assuming all of the other atoms are the same. Another consideration for acid strength is the stability of the conjugate base. So this is an example showing acetate, which is the conjugate base of acetic acid. And if you have a conjugate base that is more stable, that's going to make the acid stronger because the product, if it's more stable, the reaction is going to be more highly favored. So here we have resonance. We learn about that in Chem 101 and Chem 60. You can have your C double bond O and a single bond here. We can also take these lone pair electrons to make this a double bond, this bonding pair of electrons up here to create a double bond and then a single bond, so 2 equivalent Lewis structures. All we're moving is electron density, resonance contributors we call them. So if there are resonance contributors for the conjugate base, you're going to make a stronger acid. And this will always be true if we're looking at any type of a carboxylic acid. So remember our carboxylic acids, you have something attached to a C double bond O, O, H. So for acetic acid, this would be a CH3. So the conjugate base, so this is the weak acid, which is a carboxylic acid. The conjugate base, then in this case, H3C, C, double bond O, O minus, where we have our lone pairs. And these do indeed have the resonance contributors that we saw just straight above. So if you have resonance contributors, that increases the stability of the conjugate base, which just increases the acidity of the acid. And lastly, we're going to look at a definition of a Lewis acid and a Lewis base. Lewis acids are defined as an electron pair acceptors, so think Lewis acid, electron pair acceptor. Atoms with an empty valence orbital can be a Lewis acid. An example here is this BF3. So boron has an incomplete octet. I know it is stable with only 6 or 8 electrons. So right now we have 6. That makes it a Lewis acid. It can accept 2 more electrons. Lewis base, electron pair donor. So nitrogen has those 2 lone pairs that can make what's called a coordinate covalent bond with boron. So if we think about these lone pairs right there, 1, 2, so that new NB bond, both electrons came from nitrogen, which is acting as a Lewis base. So Lewis acids and Lewis bases, this means we can look at reactions in a way and discuss them as acid-base reactions, specifically Lewis acid and Lewis base reactions, without actually using hydrogen and hydroxide.